Good morning, everyone, and thank you, Kaneko-san, and for inviting us to speak about EdgeCortix and what we think some of the aspects that we saw in the last few speakers in building next generation generative AI. As a company, EdgeCortix, we are a young company, just a little bit over 4 years old. My expertise is more of algorithms and perhaps a lot of the aspects of computational sciences that we saw in the last slide or last speaker. So I'm hoping, what can I tell you? Where probably there are a lot more experts on semiconductors here. So I thought I'll walk you through our journey as well as some of the fundamental challenges that we see today in building silicon or semiconductors that will enable all the good things that we saw previously. We heard about Cerebrus, Allegro. They're all using fantastic tools that can enable generative AI. But how do we actually build the processors that will enable all of those functionality? So I'll attempt to break that down across 5 fundamental challenges that we see today. And then I won't attempt to answer all of those. It's a tall order, but I'll walk you through our journey through all of those challenges. If you look at AI today or machine learning, colloquially they mean the same. There is a massive explosion in terms of what has happened in the last few years. And especially in the last couple of years, we have heard about things like ChatGPT, large language models, but really it has been multiple decades of work that has really come to fruition today, where we are seeing these AI really changing how we even build chips, not just systems. So what I'm going to do in the next few slides is talk about a few fundamental challenges that we need to focus on if we want to build silicon, semiconductors, that will enable all of these AI goodness to function at a lot more effective, energy efficient, and performant manner. The first fundamental challenge is software. Just a few years ago, I was giving a talk where it was aptly titled Software Elephant in the Room. So even when you're thinking about semiconductors, there are fundamental differences between what we are used to in terms of software versus what we need to do if you're building AI silicon or processors for artificial intelligence. On your left-hand side, you have this paradigm we call software 1.0. By the way, this is not a term that I've coined. The credit goes to Andrej Karpathy, who until a few years ago was a director of engineering at Tesla. But the idea is very simple. If you look at age-old software, essentially it's a line of code where programmers like us write explicit instructions written in code, C++, Python, etc. Choose your language. And essentially you're mapping some kind of input data to written code. So you're explicitly writing down the piece of instructions. Software 2.0 that you see on your right-hand side is essentially neural networks. But the fundamental difference is that it's a series of graphical flow where you start with input data, you put in training data, and there is no explicit instructions. The code is learned. It's computed out of or discovered out of the training data. And as a result, you get a mapping of your training data and a network architectural model towards weights. Another way of thinking about this is, I think most of us have children. If you look at young kids and if you ever taught them how to learn things, shapes and colors, you'll find that we typically give them examples. We show them an example of different shapes. We show them examples of different colors. And very quickly, unlike our neural networks, they don't need, most of our kids don't require at least hundreds of thousands of samples, but they learn very quickly associations and patterns. So inherently, they have discovered this underlying code, the relationships between shapes and colors. That is exactly what a neural network is. But the paradigm is completely different. So if you think about software 2.0, if we need to build silicon for software 2.0, we need to start thinking in the manner neural networks function, where there is no explicit instructions, but you discover them through interaction with data or training data. So that's the first fundamental challenge. The second challenge is, I think, quite obvious to all of us. And we have touched upon that in the previous speakers as well, to a certain extent. The fundamental fact is that if you look at multi-core processing utility, especially Dennard scaling, it has ended. In the strictest sense of the definition of Moore's law, and I say strictest sense, if you take the very strict definition, Moore's law has ended. And somewhere around 2005, 2006, we have stopped Dennard scaling. And even if you increase the multi-core count, you are not going to get as much efficiency and utility. It has reached end of life. But it's not that all bad. There is still an optimistic view, as we saw. And if you look at even our friends at TSMC, they fundamentally believe that there is still a lot more that we can extract from Moore's law. Or in other words, Moore's law has morphed. And that morphing is taking place in the form of system scaling that you see here. So unlike the green curve, which was your typical Moore's law 2x doubling of transistor density per millimeter square every 2 years, what you see here now with the orange curve, with system scaling, with fundamental advancements in packaging, materials, interconnects, chiplets, we can still continue expanding on the system energy efficient performance. And that is predicted to grow somewhere around 3x every 2 years. Most of that data is up until 2020 and then it's projected, but we can still take that optimistic view. There is still quite a lot that we can achieve from system scaling. Nevertheless, it's a fundamental challenge for us. Now the view changes completely. If you look at AI models, it is expanding at a massive pace, which completely outstrips what we have ever seen with semiconductor scaling previously, whether that's Moore's law or system scaling. The gray curve that you see here, that's your typical standard Moore's law. The pink curve, well, it shows pink here for me, I guess the blue curve that you see, that's the growth of computer vision models, natural language processing, speech models, and that has already grown at more than 10 times compared to Moore's law. But now things get even more interesting. If you look at transformers, which is basically the new generation of models that we are today using for what we are calling generative AI, ChatGPT, that's growing at more than 100x compared to Moore's law. And that computational demand needs to be sustained. So how do you actually build processors that can drive this hyper exponential demand for computing that outstrips anything that we could get from system scaling alone? That brings me to challenge number 4. When we are building silicon, it's not just performance, but it's also memory. And as it turns out, AI requires a lot of data movements. And memory is now the fundamental performance and power or energy efficiency bottleneck that we have to deal with, especially if we are creating silicon that learns from large amounts of data. As you can see from this simple graphical depiction, there's a huge gap in terms of the growth of CPU performance or even the performance of AI or deep learning processors compared to the scaling that we have seen year on year on memory performance. In fact, there is a 50% on every year gap between CPU performance and memory. We need to radically innovate on packaging. We have talked about 3D, 2D, going beyond our current methods, 3D integrations. We have to also look at architectures that can bring memory as well as compute much more closer together. Fundamentally shift the way we process, move from typical von Neumann architectures to something different that was designed fundamentally for software 2.0. So that brings me to my final challenge, challenge number 5. Compute, memory, software 2.0, and then we need to now deal with power efficiency or energy crisis. If you look at the left-hand side, it's not a very optimistic view of AI, unfortunately. It's a fact that all our AI models. In fact, this data, I think MIT Technology Review is already perhaps 3 to 4 years old. And there has been an exponential growth since then. ChatGPT did not even exist when this data came out. So it has only gotten worse. There is a sustainability problem in terms of bringing these massive models that deals with large amounts of data. Whether you're doing training or inference at scale, you need a lot of power, a lot of energy. On the right-hand side, I try to depict this in two scales fundamentally. Performance that we can get from silicon or processors that we design versus the power that you need. If you take a very simplistic view, you can break it out into 4 simple quadrants. On the top left, I call it zone of uselessness, but it's probably a little bit too harsh. But fundamentally, it's not very useful to have processors that give you very little performance but have very high power consumption. That's the key idea. In general, most of our data centers today fall somewhere around the top right quadrant, where you have very high performance in most cases, a lot of compute, but they are also requiring a large amounts of power. I mean, for example, one of the leading GPUs in the world today in a data center perhaps singularly consumes somewhere around 500 watts of power consumption, singularly. If you put that in a massive system, you're talking about kilowatts of power consumption, while it's definitely delivering a lot of compute performance. On the bottom left quadrant, you have what we call edge systems. These are devices, perhaps like your cell phone, or even a car is an edge device. They typically have less performance in many cases today, but also consume much less power. At the more extreme end, you would have milliwatts of power consumption, and somewhere in the mid-range, you would have few watts of power consumption. Where we want to get to as an industry is what I call the zone of high efficiency. That's to your right-hand side of your bottom right quadrant, where you have the right balance, trade-off between high performance and low power. And the curve that you see here depicted in purple is not a fixed curve. That can move, it can move horizontally, it can move vertically. So we need to find architectural innovations, we need to find material innovations, we need to find system scaling innovations that all collectively allow us to move along some form of optimality across this zone of high efficiency. And in the ideal case, you want to be dynamically balancing the trade-off between your performance and power. Next, I will concentrate on how did we as a company start solving some of these challenges. I'll walk you through our experience. We heard about domain-specific architectures, and I'll touch upon that. The domain that we are focusing on is, of course, software 2.0 or AI. I will not attempt to answer all of these challenges. It's a tall order. But I'll try to walk you through our journey in that process and how we, as a young company with a smaller team that can accelerate forward this endeavor quickly. If you think about breakthrough efficiency versus performance, we can, in a simplistic manner, plot software 1.0 flexibility, so standard general purpose computing, lines of code as we talked about, or we talked about sparse matrix computations. You can implement that with a standard code, for example. That's your software 1.0 flexibility. Most general purpose processors are very good at that. And then on your y-axis, we are looking at efficiency. While we can do that flexible programming, how much efficiency, typically measured in performance per watt, or at the fundamental level, energy per operations, and then you have operations per second, so you get energy per second, so to speak. In the language of AI, we would measure this in performance per watt. When we started focusing on this, we realized very quickly that if we were to build silicon for AI, which is essentially software 2.0, that is nothing but a data flow, as we saw. It's essentially a graphical structure where there are interdependent relationships between your data as well as the operations that you perform on that data. As we saw, if you recall, in the first or second slide with transformers. So we concentrated on building a domain-specific processor where the domain now is not just AI, but it's software 2.0. Fundamentally, graphs, data flows. Whether now you apply that on AI domain or you apply that on 5G telecommunications domain, it doesn't matter. As long as you're processing graphs, you can now extract a lot more in terms of performance while constraining the amount of power that you will require. So in that curve that I talked about, if you're able to move along that curve, you can now trade off your general purpose flexibility, focus more on graphical processing, rather when I say graphical, so software 2.0 processing, not graphical in sense of computer vision, and extract a lot more efficiency. 10x, 100x, 2 orders of magnitude almost, it's possible. That's our core mission as a company. To essentially build software-defined, software 2.0 specific acceleration, where we can now achieve orders of magnitude more power efficiency, speed, or lower latencies, as well as your cost ultimately reduces significantly. If your heat dissipation is lower, your power is lower. Second, of course, if you're building software 2.0 specific architectures, it's not enough if you want to build a scalable solution. So next we looked at where is the bottleneck of AI? And it turns out data is the new oil. Data is what is driving all these AI systems. And where is this data? This data is not really in your data centers. As you can see from the statistics here, 75% of enterprise-generated data is going to either be generated, created, or processed at the edge, whether that's edge of your network or edge of your devices. So if we were to move all that performance with better power efficiency closer to the source of data creation, we minimize or reduce all the energy expenditure that we have as a result of moving data. And that's where we concentrated on the edge. So we are bringing compute closer to the source of the data itself. And hopefully that should give us a lot more scalability to tap into all that data sources, distribute our computation across an edge landscape, and benefit a lot more in power efficiency and performance. Along with that, third, we looked at some fundamental design principles for power efficient, what I call AI processes, but again, we are talking about software 2.0 fundamentally. What are these design principles? The first aspect that we focused on, again, as a very young company, is how do we create modular, scalable architectures with less complexity in their building blocks, almost like a Lego-like manner, that we can now combine together and scale massively. If we have that approach, whether we are focusing on the edge or the data center, it allows us to scale. If you take the alternative approach, where you start with a very, very large design, it's much more difficult to scale it down into its building blocks while trading off power versus efficiency. The second principle is software-first thinking. And that again goes back to my second slide. Fundamentally, if you're building silicon for AI, it's actually not so much about semiconductors, it's more about software itself. Compilers that we are all familiar with does most of the heavy lifting. So let's move as much complexity as possible to the compiler, to the software. Make the hardware as simple as possible. Let the software do most of the heavy lifting. And then, of course, you need silicon-proven IP, but that is largely solved today. It's almost a model where we can walk into Home Depot or Walmart and select multiple different types of proven silicon from our friends at Cadence and then build systems very easily. So that's another simple design principle. Fourth is, of course, you need state-of-the-art EDA tools. When we started as a young company, again, we looked at the landscape of EDA tools. What is it that enables us to reduce our time to market drastically? And that's again where we started focusing on tools like Palladium and many others that enabled us, and we saw in many cases that we did achieve considerable amount of performance efficiencies and faster time to market. And then fundamentally, there's a clear shift that we have experienced ourselves in designing silicon, smaller teams. Most of the silicon that we have created in the previous decades has required us to have hundreds of teams in the smallest case, perhaps even thousands of team members. The first silicon that we created that's already in production today as an AI silicon that can process even your generative models within very, very low power footprints, and I'll talk about that a little bit later, was just a 10-member hardware team. So you don't need very many engineers to do the hardware work. In our experience, you actually need more software engineers to be able to understand the internal functions of what is it that you're trying to create in terms of AI or software 2.0. And as a result, you get impact. You are able to create designs that are flexible, that can deal with the rapid rate of evolution of AI models. So what I mean here is, hopefully many of us have heard about convolutions, right? Now, convolutions used to be the gold standard, so to speak, in AI models. It no longer is. So if you now create a hardware that does very well, it performs extremely well, but works for convolutions, it's going to be obsolete in a few years. Well, actually, it used to be a few years. Today, it's perhaps in a few hours at the rate at which AI models are expanding. So you need to design with an inherent flexibility of operations itself. And then, of course, if you're focusing on the edge, you need high performance, but you cannot trade off speed. It has to be low latency. Process data as quickly as possible. We talked about power consumption. That's another important aspect. So it has to be low power consumption compared to a typical data center. And then fundamentally focus on software 2.0. Repeating that once again, parallel pattern data flows or processing graphs rather than explicit pieces of code. So how did we start bringing that together? Again, taking a simplistic approach here, we broke this down into a building block model where you have very simple fundamental operations. We call this dynamic neural accelerator. The key idea is you want to be able to have an inherent dynamic mechanism that can trade off power versus performance, depending on what is it that you're trying to do in terms of an AI or software 2.0 application. Second, design for flexibility. This is where, of course, your hardware architecture innovations comes in. And I think I don't need to tell this audience. In our case, we invented a simple circuit switching interconnect. You can imagine this to be like a highway that connects all the compute blocks in the most simple case. You compile statically to it, but at runtime, when you're running different AI applications or models, depending on the structural properties of a graph, it decides how to route your traffic through the network of your compute blocks, where now you can reconfigure the operations in a coarse manner such that you do not increase your power consumption, but you increase your overall utilization of your compute. The goal is eliminate as much as possible dark silicon. And when you don't require compute, depending on the application, shut down pieces of your silicon. Save and conserve power. Simple, scalable idea. And we put that together in the form of a runtime reconfigurability, where you can now reuse your data and weights. If you recall the challenge of memory, one of the fundamental aspects that we focused on here is how do we bring that memory closer to compute. So that's where innovations in even reconfiguring the memory comes in. We tried to reduce the time spent on memory operations versus compute operations, distribute memory across the network, as well as compute as much as possible closer to the memory. And then with software innovations, we started focusing on not predefining how memory works on the silicon, but offloading that to the compiler. So depending on a network that you're running, the compiler should decide how much weights would you use, the parameters of the network, how much data memory would you use, how much activation memory would you use, different types of memory that you need for a software 2.0 model. It was left to the compiler to decide rather than predefining that at the architecture level. And that flexibility has an enormous impact on efficiency. I did not forget software. As I said, software is the elephant in the room. So the second important aspect of designing the silicon in our experience was to focus on the internal structural properties of software 2.0. What you see here is a very simple analysis of our software called Mera. The key idea is you should work with all existing machine learning frameworks on the left-hand side, where you're typically defining your models in software 1.0. You're writing pieces of code. And a programmer is telling, what is your source of training data? What is your model architecture? And what is it that you intend to do? And then you left the network to learn. At that stage, the compiler at the level of the semiconductor or our chip, the processor, takes on a graphical representation. It breaks down that network in the form of certain patterns that contain inherent dependencies or relationships between the graphs. It's very much like a neural network. And then all that you need to do is understand those patterns. And here, very early on, we started using AI itself. And once again, it thrills me because we heard about reinforcement learning. So I can use that word. I was not sure whether I should use the word reinforcement learning. But that's another critical technology that we used early on, where you learn to identify those patterns. You are using machine learning and AI to discover what are the patterns that are inside these graphical structures, and you build that into your compiler stack. So now you're using AI to process AI. And with that, you get a very simple structure where you can inherently decide if you have a system with multiple types of heterogeneous processors, how do you partition all of those across them and still get the right balance or trade-off between your performance and efficiency? So key idea, software 2.0 is a data flow, and you inherently process everything as a data flow. So what did that give us? This is already quite old, but nevertheless, I thought I would highlight what we had achieved then. We brought all of this together as a simple semiconductor, simple chip, I call it simple, as an AI processor dedicated for software 2.0, but that gives you quite a lot of compute while consuming comparatively less amount of power consumption, which you can now dynamically trade off. Where in performance, we can realize up to 40 trillion operations per second or 20 teraflops, depending on at what level of precision you are processing. And you are natively processing data in the order in which it arrives. In the language of machine learning or AI, we call this batch one, which is very different from what you do in data centers. For example, if I'm trying to search through a large database, let's say a recommendation engine, all of us use Netflix, I guess, many of us, and you'll find that it gives you recommendations of movies that you should watch. Behind the scenes, there is some recommendation engine that's working. Now, the advantage of that process is that a priori, before I start processing, I have the luxury of knowing the sets of data that I'll process it on, and I don't need to process the data in real time. Edge workloads are dramatically different. Take an example of a car. If the car has some processor inbuilt whose function is to just detect traffic signals, it would be very painful if the car stops for 100 milliseconds every time, which seems like a short time, but it can have a massive impact and decides whether this is a traffic signal or not. Or in other words, you cannot process data by grouping them or batching them. You need to process data in a streaming manner. So that's another fundamental aspect of architecture and algorithms that goes into performance. Power efficiency was another major factor. As a result, we are able to achieve performance per dollar and performance per watt efficiency advantages with the combination of the software and hardware, and then fundamentally have flexibility in mind. Not create a silicon that only works for one type of AI application or model, but rather scales across vision as well as latest generative AI applications while preserving your power efficiency benefits. And then, of course, you cannot afford to trade off accuracy. One of the major aspects, I did not have enough time to talk about that today, is the role of algorithms. And we can do a lot today by trading off the different levels of which we process. For example, using representations like integer 8-bit or even 4-bit representations, we are reducing the precision of our data and processing, but many a times that impacts accuracy. So here again, we worked on the algorithmic aspects that helps us achieve that efficiency and trade-off, but we do not sacrifice accuracy, which is fundamentally important for most real-world, real-time applications. And as a result, we can create systems now that scales from chips all the way to mil-standard compute boxes. And then we put it all together with a single unified platform, again, going back to system scaling, a single unified platform in an industry-first manner where you have software all the way to silicon, where the software was designed to work across the heterogeneous landscape of processors. Whether you're mixing x86, Intel, AMD, ARM, RISC-V, you should not have to change your platform. And that system scaling mindset is what we now see as a single platform here that allows you to reduce the AI deployment time from multiple months to few days in the most extreme cases. So I'll see some performance numbers just to highlight the fact what did we had achieved at that time compared to typical GPU processing. So on the left-hand side, I'm comparing the size of such a software 2.0 specific processor compared to a same process node technology GPU. You'll see that we can achieve very similar compute numbers in terms of peak compute or teraops. But there's a big difference in terms of size. And we all know that die size is a big impact on cost. It also has a big impact on power. So while we can trade off the size of the processor, because you don't need to waste real estate for other general purpose things, you can now achieve very high performance per watt advantage, whether you're dealing with high resolution data or you're dealing with low resolution data. Even when you go to a more advanced process node, if you have the right mixtures, in our experience, of architecture, software, and you're able to co-design those together, even while preserving an older process node, in our case 12 nanometers, and you compare what we can get by moving to an advanced process node like 7 nanometer, we can still preserve considerably speed, in this example 4x better, as well as power efficiency, 7x better. This is just an example. There are applications where this gap can be as big as 20x in terms of power efficiency. And that is, again, inherently mechanisms that we can use as an industry to, again, deal with the Moore's law slowing down. Wrapping up, let us revisit the challenge number 5. What we learned in our own explorations was that it is possible to create architectural innovations, software innovations, designed for software 2.0 in mind, and create these edge processors as building blocks in a Lego-like manner that allows you to move a lot closer towards my zone of high efficiency. But the key question is that enough? Can we do better? If we now need to move eventually from the edge to the data center at some point, or even consume a lot more data in the edge, which is a fact, can we do better at the system level? And that's where we completely agree in our own journey with what we heard in the previous speaker as well. What lies beyond Moore is essentially designing these AI processors that scales from a system perspective, where we can move from monolithic single dies towards more disaggregated multi-die or chiplets. The fundamental factors continue. You're still designing for software 2.0, where you start with the software drivers itself. Or in other words, you start with a compiler. You start with the software-centric thinking, understanding what is it that you're solving for, and then you take advantage of system scaling. Second, you bring compute and memory together. In fact, if you're able to compute, in our experience, within the memory, in the memory itself, that's even better. But of course, there's still a challenge. Even with chiplets or disaggregated multi-die, as we have seen today with industry leaders, while we can scale the logic, we can scale I/O to a lot of extent, analog and memory scaling is still a major challenge with chiplets. And that's where you have innovations in packaging, 3D stacking, various methods needs to be still explored, as well as interconnects, in our opinion, becomes the major next bottleneck. So how do we actually solve those interconnect? The speed at which you connect these different dies together will become a major new innovation area to be able to truly succeed in system scaling. And then, of course, you continue with your verified IP. I call it chiplets. So it's a model that I would like to describe as moving from a Walmart or Home Depot model towards an IKEA model, where you're, rather than selecting different type of IPs together, spending 2 to 3 years designing a system on chip, you're now already getting proven, verified chiplets, almost in an IKEA manner. And that now you have an instruction set to combine these together. Create your own scalable design in a much more faster time to market, maybe moving from 2 to 3 years in less than 1 year in the most aggressive time scale. That brings me to the faster time to market, and then fundamentally significant reuse. One of the biggest challenges in our industry historically is, once we create an SoC, we create a design, it is at the RTL level. How do you reuse that? That's what we achieve now with disaggregated multi-die aspects. You can significantly reuse agnostic to the process node technology. You can mix and match, and that gives us enormous ability as an industry to move forward. With that, hopefully I've been able to give you some highlights in our own journey. I try to touch upon some of the fundamental challenges that we see, from software 2.0, memory, to even chiplets or packaging. As a company, we have a new R&D center in Kanagawa, so I welcome you if you have the time to visit us and learn more about what we are doing as a young technology company in our endeavor towards the future of building silicon for AI. Thank you for your time.
Thank you very much, Dr. Sakyasingha Dasgupta.